Now, with that as a general background, let's start approaching some of these problems. But let's make one more observation on the basis of what we just did. It's really important to notice that one of the major differences, at least in graphing between the tangent and the cosine and sine, also true for the cotangent, is that the period of these functions is not 2 pi. The period of tangent is pi. Okay, so if we add pi to this curve, which goes from pi over 2 to 3 pi over 2, we get the exact same curve with a 0 that's pi away and with the entire curve displaced by pi, going from 3 pi over 2 to 5 pi over 2. So the period for cosine and sine functions is 2 pi, but the period for a tangent function and a cotangent function is only pi. And that's going to influence our approach to thinking about the graph of these functions. So let's take a look at this first function here, which is 3 times the tangent of theta over 2 plus 135 degrees. Now, something that is a little peculiar to graphing these functions is that the coefficient, which is the vertical stretch, or 3 in this case, is a little bit less important. Not always, but very often a little bit less important when we graph tangents and cotangents than it is when we graph sines and cosines. And one of the reasons for that is that because these curves are going off into infinity, okay, we're not really changing the end destination at these points. Any constant times infinity gives you infinity. Okay, so multiplying the curve by 3 is not going to really change very much the overall appearance of this curve. Heck, it was going to infinity before, and it's still going to be going to infinity after. It does change the shape of the curve, however. And in some very difficult problems, you actually have to take into account the coefficient. And we can discuss that, but for example, in the problems that we'll be looking at today, and many of the problems that you'll have to do, that's more of a point of finesse than anything else. So to get the general idea of the x-intercepts and the asymptotes and the shape of the curve, we generally don't have to pay quite as much importance to the coefficient. However, still very important is the coefficient of x within the tangent or cotangent function. So here we see that the b is 1/2. So the variable theta is multiplied by 1/2. And the formula for period for tangent function, instead of it being 2 pi over b, is now just pi over b. Because remember, the period is only pi long. So that would be the same thing as 180 over b if we're dealing with degrees like we are here. And b, remember, what is b in this case? What is theta being multiplied by? It's being multiplied by 1/2. So b is 1/2. So the period is 80 over 1/2, which is the same thing as 180 over 1/2, which is the same thing as 180 times 2, which is 360 degrees. So our period for this function is 360 degrees. So let's see, does that help us at all? Let's go down and take a look. Well, what's the period of A? Clearly, it's a lot shorter, right, than 360. Looks like we've got about 1, 2, 3 periods in a 180 degree stretch, so that would suggest a 60 degree period. That's way too small. Let's look at the next one. This is a 360 degree period, right? If we shifted them both back left 1 square, you could see it would be going from 0 to 360. So B could be true. Okay, let's look at C. Let's see, what is the period here? Take a few moments to take a look. I think you'd agree the period is 180 here. Okay, so from this point to this point is 180 degrees, so that's a period half as long as what we need. And down here, we've got another period that's 360 degrees long. Okay, so if we shifted this to the right 1 square, and it sure looks like this is going to be about intersecting about the first square, it would give us a 360 degree period. So we've got 2 candidates, either B or D, and this is sort of similar to what we've seen in a lot of the sine, cosine, and cosecant, secant questions where we can narrow it down, but we don't necessarily get the exact answer. So how do we go ahead and decide between B and D which one is correct? Well, we can recall that the asymptotes, and I think this method works even better for tangent than it did for cosecant and secant. We can look for our asymptote. And remember, when it came to tan, let's go back and look at our tangent graph. The asymptotes are all going to be at 3 pi over 2, or 5 pi over 2, or pi over 2, stuff like that. So we've got to set the tangent equal to one of those degree measures. So let's go ahead and set pi over 2 equal to, which asymptote should we choose here? Let's see, kind of looks like 3 pi over 2, or that would be 270 degrees. Looks like something worth trying. Okay, so 270 degrees would be our asymptote. So we're going to set what's inside the parentheses equal to 270, and that should give us the theta that occurs at an asymptote. Let's go ahead and solve this. Theta over 2, 270 minus 135 is 135. That gives us theta is equal to 270. Okay, so our asymptote should be at 270. Let's go ahead and see if we can find which one of these two has an asymptote at 270. You'll see certainly it can't be D, right? 270 is right within this period, this interval between 180 and 360, and we definitely don't have an asymptote there. If we look at B, the asymptote of 270 is midway between 180 and 360, and that looks like the asymptote, right? Because it looks like the curve is approaching this from above and approaching it from below, and therefore we've got B as our answer. Now, some of you may like another method. We went ahead and we did asymptotes first, in part because we had used asymptotes for cosecants and secants. But there's another, perhaps even easier way to go about doing this with tangents. Since it's very easy to see the zeros along the x-axis, right? Very easy to see the zeros. We can actually solve for the zeros. And that's usually what I prefer to do, is to solve for the zeros rather than solving for the asymptotes when it comes to tangent and cotangent. So let's revisit our tangent graph and notice that the zeros are at intervals of whole number pi. So pi, 2 pi, 3 pi, or negative pi, or negative 2 pi, or even 0 are all zeros of the tangent curve. So we can set theta over 2 plus 135 equal to any of those zeros, and then just solve for the appropriate zero. So one of the zeros was pi, which is 180. So let's go ahead and solve for 180. Subtract 135 from both sides. That would give us theta over 2 equals 45, which means theta equals 90. Now here we're solving for a 0, and we've just found a 0 of the function at theta equals 90. Well, let's see how much easier that can be. Does function b have a 0 at 90 degrees? Obviously yes, right? Bullseye. What about d? Does d have a 0 at 90 degrees? Obviously no. So in some ways, solving for the zeros is even easier than solving for the asymptotes, and that's going to be the strategy that we're going to use to solve the rest of these graphing problems.